Hi and welcome. I'm trying to learn particle physics, and after we've done that, we're going to do leg injury prevention training. And if you participate in the leg injury prevention training, that is at your own risk. Now, this is part 3 of neutrinos. I didn't say that. No, today neutrinos with neutrinos. This is part 3 of neutrinos, I think. As long as in the 1960s, physicists measured the quantity of electron neutrinos reaching Earth from the Sun found a major shortfall, with one experiment detecting only 25% of the expected number. Okay, they said here in the sentence before that the Sun is pumping out neutrinos, as well as nuclear power stations. And now they measured the one coming from the Earth, and that one in the 1960s did measure just a quarter of the expected amount of neutrinos. What was I know all about? But we had a problem finding neutrinos, so we need a neutrino detector, did we already say. Solving the mystery involved conceding that the standard model was incomplete. Rather than being massless, as the standard model assumed, each neutrino did in fact have a tiny amount of mass. So neutrinos, we're having the electron neutrino, the Moore neutrino, and the tau neutrino. They are inside of each fermion, and they seem to have actually a little bit of mass. And yet the sum of the three neutrino masses can't exceed more than about 0.3 electronvolts, more than 1,000,000 times smaller than the next lightest particle, the electron. Okay, all three neutrinos together can have in maximal sense 1/1,000,000th of the mass as the electron has. Why is it that neutrinos are so enormously light, like an anomalously from an anomaly? So from a bird, it is not as usual. An anomaly, it is not as expected. It is not in the ordinary. It is odd. Why is it that neutrinos are so anomalously light compared with everything else is bizarre, says Frank Claus at the University of Oxford. It's as if they want to be nothing and yet weren't allowed to be. The neutrinos want to be nothing. That's interesting. What is meant here by Frank Claus is, I don't know what's meant, but it's actually, we have to take it literally, what they said. They want to be nothing, they don't have a will, but they want to be nothing, but actually the neutrinos should be nothing, but they can't have nothing. They weren't allowed to have zero mass. We have to take it, this is not a joke, as it is. They want to be completely massless, but they can't be massless. Can something exist without having a mass? Would be an interesting question. If there's a physical law saying no, and that law exists before the standard model was created, who had said that neutrinos do not have mass? That's an interesting question. So the main question: do things exist which have no mass? Do things exist with zero mass? It was the explanation of antimatter. We can't say precisely how heavy each of the three neutrinos states is. Either, besides saying the mass of the lightest state is about 0.05 electronvolt, that is because having a tiny amount of mass gives them another remarkable power. Okay, all we can say about the neutrinos is that they have less than 0.05 electronvolt. It's a complex sentence. We can't say precisely how heavy each of the three neutrino states is, either, besides saying the mass of the lightest states is about 0.05. I get it now as we can only say that it is less than 0.05 electronvolt. And that is less than a millionth of an electron. That is because having a tiny amount of mass gives them another remarkable power. They can switch between different flavors, morphing from one into another as they zoom along in a process called neutrino oscillation. Over the following decades, experimentalists gradually worked out that neutrinos came in multiple types of flavors. They are meaning the electron neutrino, the neutron neutrino, the tau neutrino, the Moore neutrino, electron neutrino, tau neutrino, and Moore neutrino. These neutrinos can change from one to the other one. Having a tiny amount of mass gives them another remarkable power. They can switch between different flavors, morphing from one into another as they zoom along in a process called neutrino oscillation. Electron neutrinos produced in the Sun's core can transform into either muon or tau neutrinos, evading our searches on Earth. Why are tau and muon neutrinos harder to find than electron neutrinos? Maybe it was set as someplace, but I don't know. And it would be interesting if something can exist, morph to something else, and then it's harder to find. But it's in nature. And it would be not an animal. It would be not an animal getting in the winter white, what is it called? White skin, or what is it called? White hairs, whatever it's called now. Wool, white wool, instead of brown wool in summer. This shape-shifting solved the solar neutrino problem, but other mysteries remained. The most vexing, okay, now they could say we can't find all the neutrinos on Earth as we want to, or should to, do only a quarter of them, because they're morphing into the other two neutrino states, and then we can't find them. I don't know why it was not hard to find them. I haven't paid enough attention, I think. This shape-shifting solved the solar neutrino problem, but other mysteries remained. The most vexing of these states from the 90s. When an experiment called the Liquid Scintillator Neutrino Detector, LSND, in Los Alamos, New Mexico, found that the antimatter versions of muon neutrinos were oscillating into electron antineutrinos faster than expected. Let's read this part again, and let's not read so harshly. This shape-shifting the most vexing of these states from the 90s, when an experiment called the Liquid Scintillator Neutrino Detector in Los Alamos, New Mexico. Okay, there's a mystery from the 90s. In the 90s they measured something, and that was done in New Mexico, Los Alamos, and it was that the antimatter versions of muon neutrinos. Muon neutrinos have antimatter versions. Are they part of a standard model? Are they big quarks? Or who is it? Okay, the antimatter versions of the muon neutrinos. They were oscillating into electron antineutrinos faster than expected. Electron antineutrinos. We have electrons, we have electron neutrinos, and we have electron antineutrinos. And happens faster as they thought it would happen. The result was confirmed by a second experiment, Mini-Boon-Me, which ran at Fermilab in Illinois from 2002 until 2017. Another set of confounding results come from radioactive decays within nuclear reactors on Earth, where you appear to produce about 6% fewer electron antineutrinos than the standard model predicts. So too many electron antineutrinos being produced on one hand and not enough on the other. What is going on? We will continue that part in the next part. My question. So if you were here for particle physics, you can go directly to the next part of particle physics. We will do now the leg injury prevention training. If you stay and participate in the leg injury prevention training, that's very good. We're bringing one leg up and we're pointing the foot down. The mushroom. And the other leg up and point the foot down. Take the leg at the ankle. Make a straight leg. Point with the knee down to the ground. So to stretching the quad muscles. Right. And take the other leg at the ankle. Straight back. Point with the knee down to the ground. And an exercise. Pine pit crawl. We're breathing in, lifting one leg up. And we're breathing out, bringing it out towards, bringing it out to the side. We're breathing again in. Out back out of the middle. Just down. Leg up, breathe in. Out to the side. Again in. And down with the other leg now. Leg up, breathe in. Out to the side. Breathe in. Out into the middle. And down. and another breathe again in, leg up, out to the side, out to the middle, and down. And now the direction, boy. Leg up, arms out, and we're bringing the arms over to one side. And over to the other side. And up the middle, head down. Now with the other leg. Arms up, and we're going with the arms over to one side. And in the middle, and over to the other side. And now, a little more advanced. Leg up, arms again out. Now arms over to one side and the leg over to the other side. Now changing leg to the outside, arms over to the other side. And in the middle, now with the other leg. Leg up, arms out, and over to one side and the leg into the other side. And we're changing. A little. Now, I don't know, it's slash and back slash. Let's do it better. Leg up, letting over the leg, flex body, hips toward back, and pressing over the inside, hands inside of the knee. What's the outside from the inside? From the inside, it's the inside of the knee. And we're doing the back slash. Leg up. And it is from the perspective of a knee the inside, and also from us the inside, so we're pressing from the inside into the inside of the knee. And up again. And the next exercise, leg up, and we're pressing the knee up and to the side. And with the other leg up, and we're pressing the hand up to the side. And now we step one leg up, again down flex foot, so that we're staying all the time airborne. And the other leg up and down. Now we're doing rolls. Leg in and out, again in. And the other leg in. And you can do now the horse or the step again, because we're doing now the camel, which is a bit more complex. Like up, back, and then moving this time also with the whole body, except of the steering wheel. And now with the other leg. In, out. And last time. And we're going to do now one even more advanced exercise. You can do one of the three previous ones. Leg in, swing it back towards standing leg, flex foot with swinging leg. The upper part of the body goes into momentum. When the swinging leg comes up, try to have a towards standing leg. Try not to fall in the abdomen. You're changing the leg. And last two. Now, trunk again, I have the ending. Next one, part everything. Out. Now we're going to close the legs. And breathe again out. And bed pose for leg into the leg. I thank you very much and next.